horizontal line, and of course we did not get that by Murphy's law. That's because the pulsar is slowing down. So over here, the period I assumed was too long. As the period slows down, the real period slows down, the pulsar slows down. My assumed period becomes just right, and as the pulsar slows down further, my period is now too short, and residuals build up again. However, by fitting straight lines through these using a square fit, I can work out the period at those 2 points there, and I worked out the period derivative to be 10 to the minus 13 seconds every second. From the period derivative, we can work out the age of the pulsar, which is 1250 years from our data, and the Chinese only saw it in 1054, that's 954 years ago. My calculation is wrong by 5 error bars. It's still impressive that it actually works. And we can also work out the surface magnetic field, which is about 10 to the 8 Tesla as advertised before. Now I should mention we did additional corrections because the Earth is rotating. So every 20 minutes, between those 20 minutes, six pulses, the Earth moved 600 kilometers basically around itself. So the telescope moved 600 kilometers. And that would introduce a time lag of 2 milliseconds, which is unacceptable because our period is just 33. So we had to move everything down to somewhere. We moved it to the center of the Earth basically, and pretend that every calculation was done from there. We also corrected for the Earth orbit around the Sun. The Earth moves at about 4.7 kilometers every second, and that's a lot, and a time lag of 20 milliseconds between every 20-minute pulses. So we move everything down to somewhere called the barycenter of the solar system. That's just the center of mass, taking into account the Sun, Jupiter, Saturn, and everything else. Now I'll talk about the dispersion measure. Signals from the pulsar travel through interstellar medium, which is usually an ionized medium, and different frequencies travel at different speeds, called the group velocity. And all the frequencies, the pulse in all the frequencies left at the same time on the pulsar. However, the high frequencies get here first than the lower frequencies according to the equation. And therefore we can work out the travel time for the pulses. The first term here would be the travel time if there were no dispersive medium, no electrons. And this term here we'll call it the dispersion measure. That's a measure of the electron density and the distance between Earth and the pulsar. And if we simplify that further, we're only interested in the time delay between the pulses. We get something which is t is proportional to 1 over nu squared. And if I got t against 1 over nu squared, I expect a straight line. And happily that's what we got for the Crab Pulsar. And using the gradient, we can work out the dispersion measure. And we found it to be 154 parsec centimeter cube per centimeter cube. Assuming a constant electron density along the line of sight, 0.03 per centimeter cube, we worked out the distance to the Crab Pulsar to be 5100 parsecs, and the real value, according to these guys, is 1700 parsec. So I'll tell you why it's different later on. We did the same procedure for PSR BO329 plus 54, straight line again, although bigger errors. Dispersion measure this time was 154 parsec per centimeter cube, and the distance was 800 parsec, which is definitely well within error bars from what this database says. And we conclude that the electron density along the line of sight from the Crab Pulsar is not actually uniform. It's obviously a little bit higher. Half a minute, so I'll tell you a little bit more. We have the most interesting things I found during this research was I realized that pulsar timing was used heavily in setting up the universal time coordinates, and they can actually measure pulsar signals down to 10 to the minus 13 seconds, which is awesome. And I also learned a lot about team dynamics during this time, and dealing with problems solving and working with other people. And that's it, gentlemen. Thank you very much.
Thank you very much, Alan. Yeah, great. Okay, can I ask you to turn off your camera, please?
Sorry.